the Python tutorials by going through this example. A spiral staircase in Python using Rhino Common. Okay. I will show the slides, but basically I'm going to reinvent it, and fortunately or unfortunately, I don't remember how we did it on this day. I'm going to think together with you, and you will see the entire process. So let me open a new file and save it in the repository. Spiral staircase. Okay. Python. Okay. Import Rhino. But geometry has RG. Now I remembered what we wanted to do the other day that we didn't do. What we wanted to do was a little example about making a grasshopper data tree that we didn't make.
Oh yeah, yes. Now I also remember this.
But I couldn't think of a very good use case for it, but this is something that often pops up in Q&A fora, so I thought I should talk about it at some point.
Actually, now that you mentioned it, I remember the question that I had. So when you talked about the data sets in Python, I didn't. So I basically just want to confirm that it is possible to make a data set with different data types within the set.
A data set with different data types in a set. Yes.
Okay.
But I wonder why should you want to do that?
It was just one of your examples in the lecture for the flow control. And I didn't know that it was possible, so that was something new. That it can contain both like integers and strings within one set.
But I think this is something that I actually never do. Like putting things of different natures in one package.
Okay, yeah.
So because of my mathematical approach to this, I kind of never do this. I know that many, even mathematical textbooks start with examples about sets and in which they put numbers and characters. But I never like these kind of examples because they give a confusing message about the nature of sets and the reason to use sets. So I never use those kind of examples even. If it is there, it's by mistake. So, but yeah, it's technically possible in Python.
Is it something that is only possible in Python? Because back in school, I think we used C++, and I don't remember it being.
No, I think there it's probably pretty much impossible.
Okay.
Because C++ and C# are very strongly typed, so they require you to declare the type of the things that you want to put in a set, in a data set, or in a data structure.
Yes.
In advance, and you cannot confuse data types with one another. So yeah, I think it's a bad idea, to be honest, to combine things. If you ask me.
It was just something new to me, so
yeah,
it's interesting.
But now that we're talking about data types, I think since Python 3 point something, it is possible to declare data types for things in Python 3. But you can guess what will happen if I try to do it here, because this is not Python 3, this is Python 2, this component. So it will probably shout at me saying that I don't know what you want to do, okay? But when we find a way, when we switch to Python 3 and real Python and using libraries of Python, remind me to show you how you can declare data types in Python.
Okay.
Because nowadays it's possible.
Okay.
Or when writing functions, when declaring variables, there is no real declaration in Python. Declaration and assignment are both done at the same time, but in any case, you can declare types as of Python 3.5 or something. Okay, anyhow.
Yes.
So
Thanks.
if you could think about, let's import it. There's no harm. Import grasshopper as gh. Okay, we will think about a reason to use a data tree. Maybe I can first show you this one and then continue with the rest, but it's pretty much independent of anything else that we want to do. And it's just a matter of convenience that we might have to use it every now and then. So if you don't mind, I'm not going to mix it with this example. Let me just focus on the geometric thinking of the geometric thinking that we need to do in order to make a spiral staircase from scratch. So let me open a paint screen and sketch what we want to do. So my goal is going to be, actually, I don't know why we call it the spiral staircase, because it should be called the helix staircase. So this kind of a curve is known as a helix. Okay, so we need to write the equations for this curve, and for doing this, I'm going to do it from scratch, and I'm going to pray or hope that I won't make any mistake. And I will use this as an excuse to remind you of a little bit of trigonometry. Yeah. So if you look at the helix from above, you will see a curve like this. Or let me do it this way. I intentionally emphasize the starting point and the end point because I want to draw this curve by using parametric equations and a concept that is known as a locus. Okay. So this circle, if it has a radius of equal to 1, is known as a trigonometric circle, in which arc length, which is this little piece of rope, is measured in radians and is equal to the angle facing the arc when measured and specified in radians. Okay, so if this is p third of radians, p third radians, this means that if you remember from high school mathematics, 2 times pi times the radius of the circle is equal to the perimeter of the circle. Right? So if the radius is equal to 1, the entire perimeter of the circle has a length of 2 times pi. And what does that mean? Practically, it means that if we order a pizza with the radius of 1 meter, it will be a huge piece of pizza. And if I say I want pi, oh, sorry, 1 radian of the pizza in terms of the angle of the slice, how much would that be roughly, do you think? If the entire pizza has a perimeter of 2 times pi, and it also spans 2 times pi radians, if I want 1 radian of the pizza, how much of the pizza is that going to be, roughly? Shall I refresh your memories? Pi is equal to?
Yeah, 314.
Yes.
6.
So, yes.
8.
So if I want 1 radian of the pizza, what does that mean?
6. Wait. God, I feel so
6.28.
ridiculous.
Yes, 6.28, but let's say 6. So 1 radian, how much of the pizza is that going to be?
1 radian of the pizza. What? Wait. Let's do it through the area of the pizza.
I said angle.
But then we take 1 radiant. How many radiants are in the circle?
Come on, this is, if the whole circle is 6 radians.
Yeah, the whole circle is, that is.
So if I want 1 radian, it's almost 1/6 of the circle.
Oh my God.
Excuse me.
Yeah.
What was 1 radian?
It's almost 57 degrees or something. Radian is the unit of angles in scientific mathematics and engineering, and it's equal to the arc length. Arc length in the trigonometric circle. The trigonometric circle by convention has the radius equal to 1. So 1 radian is actually 1 meter on the trigonometric circle, or 1 centimeter if it's 1 centimeter, or whatever the unit of the length is. Right? But it's also a unit of angles. Yeah? Does it make sense? It's a way to make angles metric.
So around 57 square centimeters.
Yeah, so we are all pretty much used to the idea of the whole circle being 360 degrees, right? So 1/6 of it is almost 60 degrees, right? So 1 radian is almost equal to 60 degrees. Correct?
Mm-hmm.
Does it make sense now? But this is a little bit more than 3. So 2 times 3.14 is 6.28. So this ends up being a little bit less than 60 degrees. Yeah? Are we okay with this? Okay. So the unit of angles is going to be radians. Okay. So the whole circle is 2 times pi radians. Half of the circle is pi radians. 1/4 of the circle is half pi half in radians, and so on and so forth, right? Pi third is going to be 60 degrees. So pi third radians is almost equal to 1 radian. We could have answered it also like this. Yeah? Is it clear? Yes?
Yes. It's just a question of which, I think, which units you wanted to hear your answer in terms of pizza.
So the question was, how big is going to be this slice of pizza? Would
So
it be fair?
1/6,
Yes.
10 degrees.
Yes. So let's do something different. Let's try to find the equation of the circle or the circular curve, let's put it this way, in terms of the location of a moving point around the circle. What is a circle after all? The mathematical definition of a circle is the locus of points whose distance to a center is equal to some number called a radius, right?
Yes.
Locus is almost a term that means the mathematical location of.
Geometrical.
Yes. So we define location with respect to some mathematical equation, okay? If this is some angle theta measured in radians, what will be this length? If the radius of the circle is equal to r, this length is known to be equal to r cosine of theta. It's another way of saying that x divided by r means cosine of theta. And similarly, y equals r sine of theta, or you can also say sine of theta is a number that is defined. This means by definition equal to y divided by the radius of the circle. This is an observation of ancient Greeks and many others throughout the history, that these kind of proportions remain the same in triangles of different radii for their hypotenuse. So it's actually an observation about triangles, that the proportions of this side of the triangle to the hypotenuse, which is equal to the radius of some circle passing through this point, remains constant and is always equal for all these similar triangles, remains the same. Similar right triangles. Hence the name trigonometry, or the study of triangles, right? And these proportions are very useful throughout mathematics. The cosine, the first proportion that I just talked about was sine, and cosine is the proportion of this side, or the side of the angle divided by the hypotenuse is known as the cosine, and the other one is known as the sine, the opposite divided by the hypotenuse, right? So when you know these proportions, and that's why in old engineering textbooks before the age of calculators, they would print out some famous sines and cosines and tangents and cotangents, which are the proportions of sines and cosines, respectively, for some famous angles, and they would and engineering students would memorize many formulas to be able to calculate the sines of other angles from the sine of famous angles because they had to memorize some. And I'm kind of from that generation, so I may remember a few sines and cosines for some famous angles. Okay, but I'm not going to test my memory right now. I'm just going to pass the intuition. Okay, so sine and cosine, we know what they are, but the question is, can we use this differently? Can we say that the circle can be defined as the locus of points for the angle theta, right? Does this make sense? Because I'm just stating the facts about the circle. Is that correct? So
Yes.
what's the point of this? The point of this is the following. Here I have a single parameter. So this is a constant. This is a constant about the circle, the radius. This is a parameter that I have. And this one is basically a spatial parameter. Isn't it? It is exactly the arc length, isn't it? So if I start drawing, let's say, going downstairs from here to here, if I look from the above, I have done something like this, isn't it? So I have started from theta equal to 0, and the positive trigonometric direction, by the way, by convention, is the counterclockwise orientation. Okay, so in this direction we count angles as positive, and in the opposite direction, or the clockwise orientation, we count them as negative angles. So if I tell you that I want the angle to be positive fourth of pi, that will be 45 degrees in degrees, right? And 2 times pi, traveling 2 times pi, or traversing 2 times pi in the positive trigonometric direction will be equal to basically traversing through the entire trigonometric circle, turning 1 round. Okay. So far, so good?
Yes.
Okay.
Yes.
So that tells us that we have a perfect parameter here, theta. And with one parameter, we can basically draw a shape, technically, as a locus of points. So we can start some points. And if we are clever enough, we can connect these points through some straight lines. And if we generate enough too many of these points, then the curve will be smooth enough to show us a triangle. Sorry, to show us a circle. That's exactly what you are looking at on the screen, right? If you notice, the circle is pixelated here. So we can generate so many points, and these so many points give us the impression that we are drawing a continuous, nice circle, but there's no such thing as a continuous domain in digital computers. So whatever we are doing is definitely about generating points. So the circle, whatever it is either an equation or it's a collection of points that fits that equation. or a locus of points. Okay? So this way we can write the parametric equations for a circle, and we can call it the circle as a function of theta. Or a curve, a circular curve as a function of theta. Okay? So this is exactly what we're going to do. But what if we want this to be a real three-dimensional curve? Then what do you think we can do? Do we have some idea for generating the third dimension in the points? So far we have two dimensions in the points. And what about the z? Okay, now give me a perfect answer. We can also figure it out throughout the during the coding experimentation, but let's first code on paper what we're going to do. Basically, now let us get a little bit more serious with what we're going to do. Every one of these points that we're going to put here is going to be the nose of one of the risers of one of the threads of the spiral staircase. Isn't it? So basically, from here to here to here to here, etc., etc., each of them is going to be a step.
And a portion of the height difference.
Exactly. Or if we think in modular terms, we can say we want our steps to have such a proportion between rise and run, or thread and rise. So what's the equation for nice steps? 2 times rise plus thread smaller than or equal to 65 centimeters. This is one of the many standards that I remember. Okay. So what do we do with this? So we have to have a good idea. So let's say we have to figure out a few things. It has something to do with the radius of the helix or spiral radius.
Putting aside the central circle that is useless in the for the threads, but we can say T is equal to R, to the radius.
Okay, I like the way you're thinking about it, but if I go back to the midpoint of what you just said,
okay,
I would say this is the worst case scenario where we don't have any thread, right? So I wouldn't count on this part of the step to be valid. So this part is definitely going to be very steep.
Yes.
How about making sure that the midpoint is okay? This part is going to be too wide.
Yes.
How about making sure that the midpoint is okay?
Yes. Yes.
Okay. So the midpoint is basically at R half, right?
Yes. And the riser is equal to the number of the points. I mean, the riser is the number which we are going to divide the height difference, which is equal to the number of the points. Not equal, maybe the number of the points minus 1.
Or Okay, let's see. So let's say if this is how we're going to go one step up, one floor up, then let's say it's desirable to have an even number of steps because we want to also have a half or even possibly a quarter of this um, um, flight of stairs. And so ideally we have a good number like, I don't know, 18 or 16 steps or something like that. Is that good? 16 or 20, let's say 20 steps. Let's say 20 steps. I'm going to use some of my favorite numbers for 3.6 meters of height difference floor to floor between two levels.
Yes.
So that's 20 steps of 18 centimeters. Okay.
Okay.
And if I choose this modular number for the height of one of the risers, then what can be a good number, relatively good number for the radius?
For the radius.
Let's figure out.
60.
So if the radius, if
60.
the radius 60,
if you take the
30, you want to reach to 30 for this point, right?
yes.
More or less. Okay. And but 60 as a width for the circle is too little. So let's say the width of the circle should be at least 90 centimeters. So I think we will be okay with the ratio between rise and run if we put 90. So if this is 90 centimeters, then we will have a very smooth and acceptable range of angles. Where can I show this? Let's say this is the situation that we're talking about. The angles at this point are basically 90 degrees, or the tangent of the theta. You can also think about it as this tangent of, let's call it alpha for the slope, should be, for the slope itself, alpha should be between ideally 30 and 45 degrees, something like that, right? So this is actually an equation about alpha, because you can find the ratio between these two, and cosine of alpha divided by sine of alpha is known as cotangent of alpha, and sine of alpha divided by cosine of alpha is known as the tangent of alpha. Tangent also gives us an indication of the slope because it's basically rise over thread. Because remember, this is also equal to this. Shall I write it down? Sine of alpha is y divided by r divided by x divided by r. These two cancel each other out, so it's basically the the rise divided by the run, or the rise divided by the thread of one single step. Right?
Yes.
This is exactly the fraction that we call the tangent of alpha. So it's a slope. Okay. This is an indirect way of stating it. This is a more direct way of stating it. But basically, you can see that if we take the radius equal to 90 centimeters, for instance, we will have a range of loci on the circle where this angle is acceptable. Well, this angle is larger than this one, and this one is larger than this one, and it's larger than this one. Do you see what I'm talking about? On a helical or spiral staircase, you don't have the same slope everywhere. The slope changes corresponding to how far you are from the center of the spiral staircase. At the very center, the slope is infinity because you have a vertical rise and zero thread. When you get farther away from the center, then the slope becomes more and more acceptable. Okay? The tangent of alpha.
Yes.
Right?
Yes.
Okay, so this is the profile of two steps that I'm talking about. Okay. So let me continue here. And let me save this. Spiral. Okay. So, let's write it again. C as a function of theta equal to x equals r cosine of theta, y equals r sine of theta. Then basically my question now is, can we write z as a function of theta as well? So my hand is a bit aching because of writing with a mouse, so I'm going to check something on paper. In the meantime, you can maybe do the same and think about a nice function of theta for z. So let me see, tangent of theta is my first guess. Tangent of theta multiplied by some number, or theta let me see. We want to make sure that after 20 steps we have traveled one floor to floor height, right? Or let's say n steps. So n times some function of theta must be equal to some floor to floor height. right?
Yes.
And n times, and floor to floor height actually means that theta has gone from 0 to 2 times pi, right?
Yes.
So exactly at that point, at 2 times pi, when theta equals to 2 times pi, the height difference will be h, and we have traveled n steps. So that means one single step theta divided by 2 times pi multiplied by h over n. Does that do the job? Because this is basically, if we straighten this out, we want to have traversed one floor to floor height after n steps. Okay. And I have to measure the steps, the step threads here. I just have to. Okay. So each of them is going to be 1/nth of the 2 times pi radius, or 1/nth of the perimeter of one circle. Isn't that correct? This is, imagine this is exactly equal to
Radius.
no, the perimeter. The exact perimeter. I have rolled it out here. Yeah. And these are the steps. This is not 20 steps, but you get what I mean. Right? I'm just unrolling the staircase. Yes? Does that make sense?
Yes.
Okay, so n steps of h over n, which is basically the rise, divided by 2 times pi, which is one full perimeter, 2 times pi times the radius. That's what I'm missing here. Wait. Which color was it? Right, so you almost see the tangent of theta here. This whole h over 2 times pi, the radius or the perimeter, is the tangent of this theta, which has to be acceptable, or alpha. Let's call it alpha. Right? So, is this correct? So if I put theta equal to 0,
Yes.
What do I get? 0 for the z. If I put theta equal to 2 times pi divided by n, if I put theta equal to 2 times pi, what do I get?
X will be equal to 1 or the R.
Z.
Z is 0.
No, when theta equals 2 times pi, 2 times pi, 2 times pi cancel each other out. H divided by
N.
it should be equal to h. When theta equals to 2 times pi, the f of theta should be equal to r. Sorry, no, h. When theta equals 2 times pi over n, this should be equal to h over n. Yeah? Am I making a mistake?
No.
So this doesn't tell me so much. Maybe I can do it intuitively in the code. So theta, this n should not be here. H divided by because this is going to be a parameter that we are going to raise a step by step. H theta divided by 2 times pi, the radius. Okay, this is my guess for now. And we're going to code it and we're going to see if it's going to work. Okay? So we're going to first make a curve, a parametric curve, as a function of a single parameter theta that we are going to generate how? Theta as member of this range 2 times pi divided by n multiplied by I such that I ranges between 0 and n, but not including n, so until n minus 1. And this whole thing is a subset of the natural numbers. Okay? So this is going to be the function that I'm going to code. Okay? And let me add an image. Okay. So, ready? So let's take in a bunch of parameters here. The radius, the height, and the number of steps from one floor to another floor. Is that good? And you're going to define this as a float, this one as a float, but this one as an integer. So let's give it a number 3.6 meters for the height, the radius 0.9 meters, and for the number of steps I'm going to put 20. Okay. Okay. Let's first draw a circle. What do you say? So we should import mathematics as well. Okay. And so let's say X list equals, well, we don't need them. Let's say points equals a list. Okay. For I in range of n, X equals R times cosine, sorry, math that cosine of what? Of theta. But we should first define theta. So theta equals tell me, I times 2 times math dot pi divided by n. Don't you agree? Shall we check our math?
Mathematically, it's correct.
2 times pi times I divided by n.
Yes.
2 times pi, yeah. But I mean, it's okay, but I would like to just make it prettier by putting these in parentheses. Okay. And to make sure that this angle is going to be a float, I'm going to put a 0.0 here to make sure that this is a float. But pi is also a float, so maybe I shouldn't bother. Okay, let's not bother with this today. Y equals R times math dot cosine of the, oh no, yes, thank you. Sine of theta. And let's say point equals RG dot point 3D X and Y and 0. And points dot append point. Good enough for now. A equals points. Let's see what we get. Hey, we have them. Okay, so we have divided the circle into 20 points.
Yes.
And now we have 20 points that hypothetically form the noses of the steps in one flight of steps.
Yes. And the formula takes n from this parameter that you said here, yes?
Yeah. Yeah.
Okay.
Okay, but we haven't yet put h into the formulation.
Yes.
Okay.
Point
So
is 0.
yes. Shall we put h also?
We have
z equals h times, what did we say?
divided by No,
h times theta divided by 2 times pi, that's h times theta divided by 2 times math, that's pi, times r. And let's put z. Hey, that's it. Now let's bake these.
Beautiful.
And let's measure the distance between here. 3.81. Maybe we have one too many. I have a feeling that we have one too many.
Wait, can I ask you a question?
Yeah.
Because I'm trying to follow the same thing that you're doing on my computer, but for some reason it doesn't work. So could you please just open the Python code once again? I think maybe okay, I have. I don't understand what I didn't do. It tells me no script to execute. How can there be no script to execute?
No script?
Like the Python thing in Grasshopper is orange for me, and it shows a warning, but there is no scripts to execute.
Okay. You know what? Let me stop sharing and you share your screen and let's figure it out.
I cannot share my screen. I'm on 2 different laptops. It's because Mac and Windows and
Okay. So read it again. Read it out.
Oh wait, now it's even worse.
What does it say?
Now it's red and it says solution exception, unexpected token off.
Okay.
I can take a picture of it.
Okay, let's hope that I also bump into the same error and then I can debug it for you here. In the meantime, maybe you can
range.
You can follow.
Wait, I think yes, I wrote in range of n, not in range. Let's see if that. Do I have to click test after I stop?
Yeah.
Yes. Okay, test. No, it's still red.
I can also put this in the chat, the code.
Yes, but it's very strange because I'm basically following at the same time as you're typing it. So, but
okay. So let me also save this in the repository. Okay, so why do you think we have one extra? 2 for the height. Let's see, how many did we get? 20, exactly 20. Okay. But do we really need 20 or do we need one less? If we just needed 4, actually we need one more. We need one more, not one less. Correct?
Okay, I just want to let you know that I don't know what I pressed, but it started working by itself.
Okay,
So it's
good news. Okay, let's get one more. And this one, Jesus, what is this? Distance, let's measure distance. 4 meters. Okay, so we definitely have one extra. So we have a little mistake in our formula here for 2 times math. 2 times pi dot r h times theta maybe we need a n. This is correct. Theta plus 1. Okay, distance. Now distance, I am hoping for your participation in resolving this issue, for mathematical participation. What am I missing here?
Let me.
This doesn't look very beautiful. So let me think. Divided by n divided by n. The theta angles are correct.
N
And if I
minus 1
put the
or n?
theta angles are correct, so we have 1, 2, 3, 4 steps. And we have now one extra point. 1, 2, 3, 4, 5 points, which is also correct. So we have 4 spans of angles of 1/4 of pi between them. You know what? Let me generate more stuff and generate this number automatically. Then we can do other things with this. So let me generate also the point at the center. Center. Centers equals bracket with the British dictation. Center equals rg dot point 3d 0 and no, this is 0 and 0 and z. Yes. And let's generate nose line equal to rg dot line from, we can make a line from a point to a point, as you can expect, from point 3D to point 3D. So from center to point, let's make a list of lines and call it lines dot append line. Okay. And let's say L equals lines. What is the problem? Aha. Nose line. We didn't have a name called line. We had name nose line. Okay. Okay. So far, so good.
May I ask a
Yeah.
stupid question?
There's no such thing as a stupid question. Go ahead.
How can I add one more parameter to this Python component?
You can zoom in and press this plus button.
Okay, thank you.
Welcome. Okay, so far, so good. Now I'm going to make a mesh face. I'm going to make a mesh out of the whole thing. So, but first of all, I'm going to make the other line as a copy of this line. Right? For which I need basically a copy of this point at the lower height. Okay, we should be very careful not to make any mistake here. Let's call it next or thread point equals what? Equals basically the next point, right? Next theta equals I plus 1 plus 1 everything There are probably better ways of doing this, but now I'm going to do it this way. Next theta next x equals r times math dot cosine of next theta next y equals r times mass that sine of next theta, and then I'm going to call thread point rg dot point 3d point 3d next x next y is 0 or no next with the same z basically. Next y is not defined. Okay, of course. Okay, no big complaint. And let me add next points, or no, thread points equals a list. The points that append that point. And T equals thread points. Okay, what is it? Thread points not defined. Ah, I have a typo here. Thread points not defined. I think I did it correctly. Yes. Okay. Well, yes, we seem to have the right points. Okay. So far, so good. And I'm going to make another line. Thread equals rg dot line from point to, sorry, thread point. Okay. Thread lines equals an empty list. Append thread line. What did I do wrong? Thread line. Ah. Okay. What did we use this for? TP T equals threads. Good. Yeah. You're almost getting there.
Yes.
Okay.
Could you please zoom a
mhm.
little bit on your code?
Sure.
Thank you.
Let me save it also. It might be a better idea to focus on my code and help me write it, and you will get the code and you can try it. Or do you prefer to try it in real time on your own machine? You can also...
yes, at first that I was following you, I understood better. So I will stop doing myself and let it better. But maybe Anna is okay.
Yeah, sometimes it's, I would say, at first I was struggling because obviously when you can pause and look at the screen, it's a little bit easy to follow. But it is nice to still try to follow at the same time, because then you learn more operations, so to say. So here's it all. But I'm already behind, so for now I stopped.
Okay.
And I decided to look later.
Okay, so let me then tell you my strategy for a few steps ahead, and then that might help you in following me better. My strategy is to create these as a straight lines, all of them, and then create a mesh with obviously with straight edges. So one line like this here, one triangular face, one quadrilateral face, one triangular face, one quadrilateral face, and then we are basically done.
Yes.
With creating this stairs, the flight of stairs as a surface, as a mesh surface. Of course, I can also make it curvy and nice, but I intentionally want to avoid doing that because we're going to be focusing on meshes. Okay.
I would, okay. My automatic idea is that it can be made into what's it called? Like so it can be repeated, so to say. So for
you mean one step that we can repeat?
Yeah, so for each stair you do one step, one triangular step, and one rectangular face. So for each level, it's 2 mesh faces.
Sorry, say it again.
Yeah, so for each level, we are creating 2 mesh faces, one triangular, one rectangular, and then we can connect it to the Z parameter. And
yeah, you're absolutely right. I mean, it might be a better idea or a good idea, obviously a different idea, to generate one step as an object, even as a solid object, and then by using transformations, transform it and copy it, or basically translate it in the language of linear algebra, mathematically translate it or move it or copy it effectively from one location to another, to another, to another.
Oh no, that's not what I meant, but that's actually also a good idea.
But that's a very construction-oriented idea. I wanted to make it a little bit more mathematical for now, just as a surface, and then we think about how do we make it. But maybe you meant something different.
No, I just remember that you mentioned also before that when you create a mesh, it's also important which way you're creating it. I'm not sure if it's
orientation, you mean?
Yes. So that's why I guess creating it from points would just make more sense in that way than creating it from a surface. Because do you understand what I mean?
But for creating a mesh, you need faces, definitely.
Can't you create a mesh from points?
Yes, you can, but again, you need to create faces. It's like weaving a fishnet, right? You need to know in which order and how you're going to generate the faces. Let me paint it here. So,
You mean like so it understands the plane you're working at?
no, it has nothing to do with the plane. The same way I create this little loop here, I should put them into a mesh face with this order so as to create one triangle, one triangular face. And then if these are the other 2 points for the riser, I want to create another mesh face also facing outward
Yes,
in this
yes.
order.
You mean the mesh face, not...
Yes, mesh face. Yeah.
Yes. Okay, I misunderstood you. I thought you create a different type of face and then you apply mesh to
No.
basic. Yes.
So it's important to create these points in the right order.
Yes. That's exactly what I was talking about. Yeah, I think maybe the way that I am imagining it right now is all from... I immediately start imagining the way to create different data sets and basically organize them in the way so this process can be... Well, yeah, so these faces can be generated from the data sets.
Yeah, there are definitely better ways.
Yes, but I mean, what I mean is this is immediately where my mind is going, so that's why it takes me some time to understand the way that you are trying to do it. But yeah.
This is basically my next step to create these faces. And then by creating the faces, create a mesh.
Yes.
Yeah. So maybe I can so right now I have all the points that I need for the mesh. Yeah. So I can create it as such. Mesh equals to rg dot mesh. Mesh dot vertices dot vertices. I remember this add vertex or add. Let me see. Point. See. Doesn't complain. So add breadpoint. You know what? I'm reaching the limit of using this loop. So maybe I should write it in another loop because I need the next one basically. Or I can just use the next point as, where is it? Next Z also equal to right? Equals rg dot point bd 0, 0, next z 0, 0. Okay. So far I've added the point as the first one. Maybe I should have first added the center. Center 0, the point 1, then the third point 2, then I have 0, 1, 2, and then I have the next point, and then the next center.
Okay.
Okay. And too long, better. That faces that add face 0, 1, 2. Faces 0, 1, 2, and then that will be 2, 3, 4, 0. 2, 3, 4, 0. Okay. Mesh surface equals meshes. Yes. Perfect. Is it good?
Yes, but I thought that when you were setting the order of the faces, I thought that you're going to make the whole each of the whole steps, but it seems that each step only has the facing and the thread surfaces. Yes.
Yeah. I'm taking a very minimalistic approach to
Okay.
what the flight of stairs is. It's just a surface, in my opinion, for now. How we're going to make it, that's a different story. So I'm keeping it simple for now.
Yes. Modular thinking.
Yeah, but that is true. I mean, if we really want to get into a way of building it, then we have to think about the different components differently.
Yes.
So let's think about alternative ways of doing this, and for now we can call it a day. I think I wanted to keep this within time because this is one module.
Because last time we discussed that it will be kind of 2 exercises. The first one is just creating a spiral staircase, and then the second one was to make it modular. So then if
that requires much more time. Yeah.
But no, what I mean is if we make it from surfaces right now in such a minimalistic way, will it be possible to, so to say, continue this exercise and make this particular staircase into being modular, or will it have to be?
Yeah, that's my idea. And by the way, now it is modular, so each of them is a separate mesh. But maybe it's not the best division of this into subsurfaces. But we will have time to think about different ways of doing this.
Okay.
That can be our assignment, yes.
Yes, yeah, indeed. And let me also give you another assignment to figure out what to do to get to the right height for this, because we have 1 or 2 steps too many. Yeah?
Okay.
So then I will call it a day for now. If there are no questions, no burning question for now.
No.
No?
For now.
Okay. Okay. Good day to you. So let me stop sharing.
Yes.
Yes. How was it?
It's still recording.
Oh yeah, still recording.
Okay. Let me see. Stop.